Okay, thank you. Thank you very much for the kind intro, and very happy to virtually be here. Great to see you in the audience, the physical audience and the virtual audience. So today, I'm going to be talking about an alternate scaling route for AI via probabilistic programs. And for this, in the context of this workshop on tractable probabilistic models, my hope is that this talk will surface some settings where the tools from the tractable probabilistic modeling community are proving quite effective, and also some settings where, as we attempt to scale AI using probabilistic programs, we're running into either practical limitations or issues which seem like they may be fundamental limitations of the approach. And so my hope is to stimulate discussion and reflection along that whole spectrum of tractability. I want to highlight that the work I'm presenting today has been done by a number of wonderful students and colleagues and staff in my group, but I especially want to highlight Firas Saad, who's done a lot of the work that most directly builds on probabilistic circuits that you'll hear about today, and he's starting at CMU in 2023. I encourage you to check out more of his papers and write him if you're interested in getting involved. And I'll also be describing some results from Nishad Gafoskar's work on inverse graphics using the GEN platform that was originally created by Marco Cusimano-Towner. Okay. So the outline of my talk. So I'll start by giving a brief high-level view on the scaling route for AI, kind of view from a bunch of faculty at MIT who are all collaborating around probabilistic programming and intelligent systems. Then I'll go through a few examples which try to sort of highlight a spectrum of tractability and intractability, and some of the distinctive AI capabilities associated with each. And then at the end, I'll spend a few minutes talking about a theoretical lens on tractability that I hope stimulates some discussion and reflects sort of how I'm contextualizing some of the engineering results. So the core problem that's motivating a number of us and especially my group at MIT, is the question of how is it possible for intelligent systems to really achieve human levels of robustness, generality, data efficiency, and energy efficiency at the same time? And then of the intelligent systems that might be able to do that, which ones best explain subjective human experience and quantitative data about behavior in the brain? And there are a number of us pursuing these questions in the context of two broad domains of intelligence. So the first is common sense. You can think of that as the knowledge about people, objects, and places that almost all humans acquire in just the first couple years of life. So that includes the knowledge that allows the toddler in this video, which some of you may have seen already, to make a really remarkable inference to spontaneously generate a helping behavior having correctly inferred the goal of this adult, even though he failed to achieve it. The second broad domain, where we've actually done a lot of work drawing directly on tractable probabilistic models, is in data-driven expertise. So helping adults bring together domain knowledge and data. For example, in this project, data on millions of children who are at risk for various forms of malnutrition, to try to make more data-driven policy recommendations. So these are two broad domains of intelligence that we'd like to model and augment. And the core conceptual thesis that's guiding a lot of this work is that we need new computing abstractions that are up to the problem of addressing our fundamental uncertainty about the structure of models that approximate the external world. So the tools of computer science have developed many kind of mature techniques for starting from a known ground truth world state and laws and simulating the sense data that an agent would be likely to receive in that world. But the problems faced by intelligent systems are far harder. Intelligent systems somehow have to make sense of that sense data using approximate mental models. They have to infer the structure of the world, account for their uncertainty about it, and also account for the uncertainty that they have about the laws and even the structure of the laws by which the states of the world evolve. Now, confronted by these substantial challenges, it's maybe not surprising that there's been a lot of effort and also a lot of progress, especially recently, kind of pursuing an approach that attempts to circumvent some of these problems by training ever larger end-to-end neural networks that map from data to ultimately to actions, whether these and I think this frame can be used to help understand, many of the domains where large neural models are being applied. But we'd like to implement AI systems that more directly account for the uncertainty of the structure, the uncertainty in the content and structure of models that approximate the world. So to do that, we'd like to draw on the neural network toolkit, but also go beyond it in some important ways. And that's what motivates probabilistic programming for us. So we see probabilistic programming as a unifying framework that allows us to combine some of the key strengths of symbolic, probabilistic, and neural approaches to modeling and inference. So of course, it's going to be very important to learn models from data, not just handwrite probabilistic programs. And to use probabilistic programs as generative models in which we can do inference. But we'd also like our probabilistic programs to be able to exploit concise symbolic abstractions, compositional representations, and modularity of modeling and inference to achieve robustness, scalability, and automation that seems maybe hard to achieve using just the probabilistic and neural toolkits on their own. And maybe the most important reflection of sort of where that thesis is getting is that I think really only in the last couple of years, we now have several application domains: 3D scene perception, common sense data cleaning, and automated data modeling from time series and multivariate databases and data streams, where really, again, only in the last couple of years, there are now probabilistic programming systems that outperform state-of-the-art baselines that draw heavily on machine learning and deep learning on benchmark problems that are grounded in standard problems in each of these fields, as opposed to benchmarks sort of defined very carefully by the probabilistic programming community. And I'll be going into a couple of these examples in more detail in my talk today, and talking about sort of where there are entire models or components of models that are tractable in the sense of this workshop, and where there aren't, and what other senses of tractability might be important. Now, for people who maybe aren't familiar, I think there are two key ideas in probabilistic programming that's important to keep in mind. The first is that in probabilistic programming, we're going to represent models as generative programs that make random choices. So not just as networks or circuits, but as executable code. And the second key idea is that we're going to represent operations of inference and learning as metaprograms that operate on generative programs, and sometimes also produce generative programs as their outputs, as in structure learning, which we'll see in just a minute. And there's kind of two broad categories of probabilistic languages that are important to keep in mind. Many people have focused on probabilistic languages that attempt to provide automatic inference. But there's also other languages that attempt to provide programmable inference and target a much broader range of problems. And you'll see some examples of both in this talk. Now, this perspective of using programs to represent models has turned out to be a unifying idea that allows a common representation language to compactly encode models from a broad range of AI formalisms and application domains. And I'm just showing a few on this slide. And I'm highlighting in yellow application domains where the underlying model families were tractable in the sense of this workshop. And in cyan, I'm highlighting examples of intractable models that were implemented in Gen, where approximate inference was necessary. And so, one point I'd just like to make at the start is that it's clear that, tractable models play an important role, but also that they don't capture all and many of the most important models we'd like to work with. So my hope is that this sort of helps to stimulate some research in this community to understand that gap and sort of where it can be closed and, what to do if it can't. And as we go through the rest of this talk, I'd really like you to keep in mind, an informal view on what I think of as one of the most fundamental trade-offs in computer science that constrains AI engineering, which to me seems inescapable, and certainly certain theoretically rigorously formulated versions of it are inescapable, which is that in computing, there are these trade-offs between the generality of a representation language, the degree to which the problems that it poses can be solved automatically, and the guarantees about accuracy and efficiency that are possible to achieve in the formalism. Yeah, to speak loosely, one might say, of these three, you get to pick two. And you'll see that tension throughout the talk. And I think that's deeply related to both why I'm optimistic about tractable models in some areas of AI engineering and why I think they're going to be insufficient for the whole picture, at least when grounded in our current definitions of tractability. Now, to navigate these trade-offs, we've been building a stack of abstractions for probabilistic computing that emphasizes probabilistic programs for making various trade-offs about modeling and inference, but extends both above and below to include domain-specific languages for common sense scene understanding and expert systems. So you'll see some examples in this talk, although I won't go into much of the PL aspects, as well as platforms that help navigate and encode trade-offs about automation and expressiveness, interoperate with deep learning fabrics. And all of this machinery can run on commodity hardware, but also we've increasingly found the need and the use for custom hardware fabrics that can lead to much lower energy requirements for probabilistic inference. So we see probabilistic modeling and inference formalisms as providing kind of crucial intermediate representations in this stack for AI engineering. Okay, so let's look at some examples, starting with structure learning of tractable models from structured data. This example is implemented using Gen. It's an open source probabilistic programming language that you can read about and you can download online. And Gen's, I would say, sort of at the early stages of escaping the academic environment. So it's the basis of partnerships with a couple of large tech companies now. And it's being used in courses at a few universities in the US, Canada, and Japan. Still very much early days. So the problem we're going to look at, this is drawn from work by Faraz Saad, is the problem of learning the structure of tractable models for time series. So can you sketch in the air with your finger the structure that you think explains this time series data? Okay, so I see some people, it looks like sketching, like a periodic structure, maybe with a linear trend overlaid. So how can we learn a probabilistic program that accurately models this data? So first, let me show you that it is possible to do that. So here you're seeing the data points overlaid with the predictive distribution from the probabilistic program on the right, whose structure and parameters are changing as new data points come in online. And we can see that, after a few repetitions, the structural learning algorithm is able to converge to probabilistic programs that capture the qualitative features that many of you picked out by eye. Although initially it's quite uncertain So for example, right now, it's not completely certain about whether the periodic trend will keep repeating or whether the amplitude will change, but by this point, it's sort of fairly confident and also confident in the linear trend. So let's look at this example in a little more detail to see the parts that are tractable and the parts that aren't. So what you're seeing on the right is the source code for a probabilistic program that takes as input some time points and includes a variable called DSL program here. That's just this funny expression, linear 1.0, that's going to capture the structure of the time series. And I'll say more about that in a minute. That's used to calculate a covariance matrix. So this DSL program is really just specifying the form of a covariance function for a structured compositional Gaussian process model. Like you may be familiar with from work by Zubin Garamani and James Lloyd and Dave Duveneau and many others. It's an important class of tractable probabilistic models. Now, given the covariance matrix, the program then samples a noise level and then generates random arrays of time series values by sequentially unrolling the Gaussian process that's specified by the given structure or covariance to generate from the appropriate normal distributions for each variable x sub I. So if we run this probabilistic program once, we might get a realization that looks something like this. And here I'm just highlighting two of the green dots, which might correspond to particular realizations of x sub I and x sub j at times t sub I and t sub j. And on the bottom right, I'm showing one trace of the probabilistic program. That is an assignment of values to all the stochastic choices made by the probabilistic program during its execution. But if I run it again, I might get something different. Maybe this time I get a much less noisy function. If I do it 9 times, you can kind of get a sense of the variability of this one probabilistic program. And if I start changing the structure, for example, to include a product kernel of linear and linear trend and periodic overlay, then I get realizations like this. Or I can have a DSL program that includes a change point, where to the left of x equals 0.5, the function's constant, but perhaps noisy, and to the right, there's a linear trend. And that generates functions like the ones shown here. So here I've defined a class of tractable probabilistic models, which compile to large Gaussians, but whose structure is parameterized by small symbolic expressions. So the structure learning problem then is to do inference about the structure and parameters of these DSL programs and the noise level. And that's what you're seeing in the original structural learning animation, is an online resample move sequential Monte Carlo algorithm for doing structural learning of this class of probabilistic models. And we can generate an ensemble of learned programs to try to characterize uncertainty over the structure as well as the predictions. So that's what you're seeing here, where the trends in the predictive distribution, I think, more closely match what you may find appearing in your mind's eye as you stare at the data. Now, an interesting feature of this structural learning approach is that it can handle exogenous changes. So it turns out the data you were seeing is airline passenger volume data. So it's instructive to see what happens when we extend the time series further to include the early stages of the COVID-19 pandemic, where there was a rapid drop in airline travel. And so that's what you're seeing here. Where all of a sudden there's a drop and the system is able to infer very rapidly that there's probably a change point and that predictions about the future don't look like the past. And it's important to note that this kind of flexible characterization of structure and adaptation to change goes beyond the capabilities of strong time series forecasting systems that are widely used in industry, such as the Facebook Profit structural time series modeling system, which is both less accurate, which is less accurate than our system, even when it's extended to include change point kernels explicitly due to challenges with the estimation. And it's a little bit faster. Facebook Profit's a little bit faster, but the runtimes are comparable. A couple seconds or a few seconds in both cases. The results from online structural learning are significantly better than the neural profit extension to Facebook Profit, which is both significantly slower and really struggles with the change point. So this type of structural learning of tractable probabilistic programs can be implemented in Gen with massively less code than earlier generations, such as the automated statistician that used MATLAB and Python and required all the details of the model and inference to be implemented by hand. And the performance of that's achieved using probabilistic programming is significantly better than previous probabilistic programming systems now, but also competitive with hand-coded implementations that have been optimized reasonably carefully. So let's look a bit at the part of the probabilistic program that's intractable. So the way we fill in the holes in this probabilistic program is this DSL program is generated by another probabilistic program. So what you're seeing here are random realizations from this recursive stochastic function generate random DSL program, which is generating expressions and the time series that might be typical given that covariance function expression. And this function generate random DSL program is a stochastic recursion that generates an abstract syntax tree by choosing a type of covariance function, generating parameters, and recursing if needed. So here we have an intractable probabilistic model as a prior over tractable probabilistic models. I'll point out that even though this structural learning problem is not easy, and it requires approximate inference, it's possible to scale much, much better than you might expect you would with MCMC approaches. So for us, Saad has done some great work showing how resample move SMC algorithms can be substantially faster by processing data one at a time and converge both more reliably and much more quickly in absolute terms. And this template has been implemented, especially primarily for us, for a range of data types: time series data, panel data, cross-sectional data, relational data, where we can go from data to probabilistic programs in tractable languages that we can then use with exact inference that's available for these tractable languages to answer a broad range of questions: how to make forecasts, how to find anomalous data, how to calculate probabilities, how to generate synthetic data. And so I'll take that set of capabilities into a second domain of structured databases and fairness verification for my next example. So the core language we're using as a common compilation target for all these structural learning problems is called the sum product probabilistic language, which we see as an interesting unifying intermediate representation for many, although certainly not all, tractable probabilistic model families. This is again work from Faraz Saad. And the basic idea in SPPL is to take probabilistic programs and compile them to a new class of probabilistic circuit that's derived from, but extends some product networks, and then to use PL techniques to improve the scalability of exact inference so that one can get simulations and conditional probabilities efficiently. And I'll just briefly highlight some of the features of SPPL that might be interesting to this community. So the first is it introduces a class of probabilistic circuit called a sum product expression that has some interesting new capabilities, including support for numerical and logical transforms, conditioning on point-wise and set-valued constraints, and careful semantics for treating hybrids of discrete and continuous random variables that are needed for these kinds of applications. SPPL provides sound symbolic inference for a broad query class, and it also leverages PL techniques for fast optimization of the learned circuits to compress the circuit size, which is essential for many applications. And its basic architecture reveals something about the problem of how to take general probabilistic programs in languages with appropriate restrictions and compile them to probabilistic circuits. And it's worth noting that it's possible to do structural learning of SPPL programs for other model families. So here I'm just showing a schematic of rows of a database table streaming in one at a time on the right from a probabilistic programming platform called InferenceQL. And on the left, I'm just showing a visual representation of uncertainty over a large sum product expression at many levels, including how the columns of the database factorize, where the modes of the distribution are, and what the parameters of the underlying distributions are. And there's some references showing the components of the system and the structure prior in the bottom right. So I'll just briefly reflect for this community that this message won't be surprising, but of course, as we all know here that this idea that probabilistic circuits might be a useful compilation target draws on a long tradition of symbolic knowledge compilation in AI, pioneered by many people who've been involved in this community for a long time, and sort of the AI communities that it kind of grew out of. Especially, of course, work by Darwish and Decter and Poon and Domingos and of course many others, Guy Vanderbroek, and sort of many students of many of the people listed here, among others. And this community has done a lot of really wonderful work that we're building on very heavily, to sort of understand what types of queries can be solved exactly in polynomial time in the size of the circuit. Of course, there's this challenge we encounter, which is sometimes the circuit may be quite large. So SPPL uses PL techniques to try to compress the circuit when possible. But in some cases, a large circuit may be inescapable. It's worth noting that this idea of structural learning combined with some product expressions and the SPPL language makes it possible for us to imagine, I think, an interesting scaling route for tractable models. So what if every database table came with a tractable probabilistic program that modeled its joint density? We've built structural learning systems that are tightly integrated with SQL that have started to make this kind of thing possible. And this plot's showing a range of data sets with real data and next to synthetic data from tractable probabilistic models whose structure has been learned from these diverse data types. And you can read more about this in one of our papers. So one thing that one can do as this capability becomes more widespread is start to leverage sort of the tractability of the underlying models to provide rigorous answers to really important questions. So for example, fairness verification of machine learning algorithms applied to that data. So there's a well-known challenge, which is that machine learning systems that inform hiring decisions can be quite biased and discriminatory. It's been especially well documented that this has happened resulting in systematic discrimination against women. And sort of these challenges have motivated a careful consideration of techniques for how to analyze machine learning algorithms for various notions of fairness. So, for example, one might like to be able to certify that the probability of hiring rejection rejection change too much depending on the minority status of a candidate. This is a particular notion of parity from the fairness community. And using the tools that I've illustrated in this talk, you can learn a resume generator as a tractable probabilistic program that provides input to a decision tree program that's also a tractable probabilistic program in SPPL, and analyze it for fairness using exact inference. And as I mentioned earlier, this gives a potentially interesting route for responding to some of the really serious challenges, including gender discrimination that are arising in sort of real world machine learning deployments. So for us, was able to show that this approach, by using tractable probabilistic models as the intermediate representation, yields significant speedups, ranging from 20x to several thousand x, relative to a range of strong fairness verification systems that have been proposed by other researchers. So this represents, I think, one of the applications where sort of we're using the most power that we've been able to so far from tractable probabilistic models. Okay, so I have about 10 minutes left. Perfect. So let me now talk a little bit about a setting where I think it's very hard to avoid intractability, and then close with some discussions about a theoretical lens. So we've been applying probabilistic programming to 3D scene perception, as I mentioned earlier, and this is work that's been led by Nishad Gothoskar, and maybe best reflected in our a paper on the 3DP3 system for 3D scene perception via probabilistic programming from Europe's 2021. The task we're looking at in this work is to go from input RGB and depth images to scene graphs and object models that can be used to reconstruct a cleaned up version of the input depth channel. So we'd like to go from the data on the left to the symbolic and geometric representations on the right. I'll just briefly try to give you a sense of where we've gotten and what problems still remain. So the good news is that it's possible to do this. It's possible to do this in about half a frame per second. So I'm showing results from 3DP3 on the bottom and results from Dense Fusion, a state-of-the-art deep learning system, on the top. Now, these results are designed to sort of highlight some of the failure modes of Dense Fusion. I'll show quantitative results in a minute. But I think it's encouraging that we're able to use a structured probabilistic program to detect and correct many of the kinds of large kind of non-commonsensical errors that deep learning systems make on this problem, like positing objects where there's maybe where it's visually obvious that there's nothing. And it turns out that this pattern holds up quantitatively across thousands of cluttered indoor scenes from the standard YCB video data set used to benchmark pose estimation systems in robotics. Now, it's worth noting that the results from 3DP3 still leave a lot of room for improvement. There are some objects and scenes where it fails. So, and I think those failures reflect both model misspecification and approximate inference failures given the current parameters of the inference engine. So there's room for more tractable approaches, maybe in principle, to do better. But let me highlight a couple of the challenges. So first, here I'm just showing a schematic of the generative program for this application. So in 3DP3, there's a prior over shapes so that shapes can be learned from just a couple real world examples. Then there's a prior over the structure of scene graphs. Then there's a renderer. Then there's a noise model for generating point clouds. So if you think about the dependencies that are introduced by this generative process, there's explaining away at many, many levels, at pretty much every level of this model. If you remember, the basic kind of pattern of explaining away from, noisy or Bayes nets, there's fundamental challenges for exact inference in the presence of explaining away in distributions that are, at least in principle, highly multimodal. Of course, in practice, many of these distributions don't seem to be particularly multimodal as best as we can test them. But anyway, I think the need to scale to models with a lot of explaining away is going to present a challenge for the tractable probabilistic modeling community. And I wanted to make sure I presented it in those terms. Another challenge is that even the tractable subcomponents of these models, like the mixture models we use for depth point clouds, are actually intractable in practice for real-time inference. So, in 3DP3, there's a mixture model where for every depth point in the generated rendered scene, there's a mixture that determines kind of what observed points might be explained by it. But if you have data with thousands of points coming in real time, it's too slow to exactly sum out all the mixture components. So in fact, we've been doing some work on fast pseudo-marginal approximations to these scoring operations, which use, important sampling estimators that, are unbiased and seem to be pretty low variance in practice. So for example, Alex Lev, another wonderful student in the group, has been working on a sound language for safe pseudo-marginal approximations to densities called procs, which can achieve pretty substantial speedups with only small reductions in the acceptance rates of the underlying Monte Carlo algorithms. Okay, so let me just spend the last few minutes kind of taking stock from a more theoretical perspective. So we've seen this set of examples on a spectrum of tractability. Let's maybe reflect on this in the context of computational trade-offs between generality, automation, and functional metrics like accuracy, efficiency, and reliability. So probabilistic programming invites us to consider a very broad family of probabilistic models, indeed all computable probabilistic models. So let's look at these trade-offs and tractability from that lens. So I want to start by just highlighting some really wonderful work by Cameron Freer, a research scientist in the Probabilistic Computing Project, who with Dan Roy and Nate Ackerman tried to ask the question, so to what extent can probabilistic inference be automated in general? So when are conditional distributions computable? And this is kind of a very fundamental building block for many notions of tractability. And so the first result is, maybe unsurprisingly, you can't compute posterior distributions in general, even if the prior unlikelihoods are computable. But maybe I think even more interestingly, if the likelihood model is sufficiently noisy, so when it includes independent computable noise with a smooth bounded density, or when the conditional density is positive bounded and computable, then actually the posterior is computable. So that means that, for the level of tractability captured by computability, inference is actually computable for an extremely broad class of problems, loosely where data is noisy, like arises in robotics and data science, and many aspects of AI. So now let's look at approximate inference by sampling, and sort of a next scale where we might be interested in tractability. So I want to highlight a really important result by Ma and colleagues from Berkeley, proving that sampling can be faster than optimization. And scale sub-exponentially in the dimensionality of a latent variable inference problem. And I won't go into the details, but this result is situated in a very interesting discourse in theoretical computer science that shows that in the worst case, sampling is easier than computing probabilities. So I think this invites the question of models with tractable samplers, where we might get interestingly different answers than models with tractable conditional probabilities. And in fact, in the non-convex setting, so even though in the convex setting, optimization and sampling are efficiently reducible to each other, in non-convex settings, actually there's strong separations, some that are favorable, in some regimes that are favorable to sampling and some for optimization. I think there's important notions of tractability to be captured here. And in fact, we've been studying the limits of trade-offs between approximate and exact sampling in terms of sort of minimal entropy sampling and optimally time, space, and memory efficient approximate sampling in a couple of papers. Again, this is chiefly work from Farhad and Cameron Freer, but sort of studying the trade-off. And it seems like there's a really rich regime where there's important trade-offs, practically important trade-offs between entropy, time, space, and approximation error for samplers.
So,
okay,
Vikash,
so this is my last slide.
Okay, cool.
So I hope this gives a sense of how tractability and tractable probabilistic models are a central tool for us, and also where some of the limitations might be. And if you're interested, please reach out. And I especially encourage you to reach out to Faraz Saad, who's starting a new lab at Carnegie Mellon University, where he's joining the faculty in 2023. But you can also reach out to me if you're interested in these topics. Thank you.
Thank you. Thank you, Vikash, for this very interesting talk. If you have questions and you're online, then please just like type the questions in the chat. And I think we have time for 2 questions. So I'm going to take first a question from the audience.
Right. Hi, Vikash. Antonio's here. Thank you very much
Hello.
for the super interesting talk. Can you hear me?
Yes, I can hear you.
Okay. So I was wondering if, I mean, the results you were discussing in your last part of the talk, to my understanding, you are comparing essentially sampling against, let's say, other kinds of approximate inference, like perhaps optimization, like variational inference in your graph when you add EM, for example.
Sorry, just to be clear, this graph is from Ma and Jordan's work, not mine. I just think it's very important. And yes, this is comparing a kind of a Langevin type sampler to an EM algorithm.
Okay, yes. And in the other comparison, I mean, it was still, yes. So in the next slide, perhaps. Yes, so you were essentially claiming that sampling is often easier than computing map estimates via optimization, right? So I wanted to make sure that perhaps I understood this correctly. So if I have a model that allows me to compute exact map estimates, that should be, of course, faster, right? So in your assumption is that you need also to approximate the map via optimization, right?
Sorry, so what I'm saying is that there are problem classes where exact map estimation is exact optimization or exact map calculation is provably hard.
Yes.
But sampling is easy.
Yes. That's
I mean,
totally
subject
true.
to the usual
Yes.
and vice versa.
Yes, yes. Yes, there
So-
are these classes and one model can be tractable for one and not the other. So
Yeah.
do you have a recommendation on how to automate, in a sense, also the discovery of this given a probabilistic program, right? So if
Yeah,
you can
well,
translate that a bit, change that little bit to get into a tractable class for the map or for the sample, the sampling, if you need to do one or the other.
Yeah, I mean, I guess I'd say, so there are, of course, limits, theoretical limits on the extent to which that's possible too, because determining tractability is also intractable. And we, we of course ran into this, as well known in this community, but we ran into this in the SPPL compiler. So I think it's maybe easy to identify coarse heuristics that are useful in practice. I think that's a very important activity, especially for understanding the regimes where optimization or sampling might be more or less practical. But, I guess I'll just say, since, there isn't much time, I really want to highlight that, to me, this slide and the explaining away challenge is the big question I have for the tractable probabilistic model community. Because I'm very happy to use tractable components and to learn as an engineer sort of when I can use them. And I think there's, of course, a lot of room for tools that identify tractable surrogates to intractable problems that are only approximately equivalent, but are maybe useful as proposals. So I'm optimistic about all of that. But I'm not optimistic about this problem. I think there's some other missing notion of tractability that's closer to the intuitive sense of the word and maybe not the formal sense that's been studied in this community so far, that's needed to explain how is it possible for vision to be so robust and so fast, despite the fact that there's explaining away at every level. And I think we ignore this problem at our peril. Okay.
All right, thank you. Are there any more questions to Vikash? We have time for maybe one more question. Otherwise, I would say we thank the speaker again. Thank you, Vikash.
Thank you very much.